In this video, we're going to be continuing to talk about random variables and probability distributions. Specifically, we're going to be talking about using the normal distribution to approximate a discrete distribution. So suppose the probability distribution of a discrete random variable x is displayed in the histogram below. Well, the probability of a particular value is the area of the rectangle centered at that value. Often, a probability histogram can be well approximated by a normal curve. If so, it is customary to say that x has an approximately normal distribution. Now suppose this bar is centered at 6. The bar actually begins at 5.5 and ends at 6.5. These endpoints will be used in calculations. This is called a continuity correction. So let's let x be a random variable based on n trials and success probability p, so that we have that the mean is n times p and the standard deviation is the square root of n times p times 1 minus p. Now, if n and p are such that your n times p is greater than or equal to 10 and your n times 1 minus p is greater than or equal to 10, then x has an approximately normal distribution. Let's do an example. Premature babies are born before 37 weeks, and those born before 34 weeks are most at risk. A study reported that 2% of births in the United States occurred before 34 weeks. Now suppose that 1,000 births are randomly selected, and that the number of these births the number of these births that occurred prior to 34 weeks, which we'll call x, is to be determined. So can the distribution of x be approximated by a normal distribution? Well, we're not sure. We need to find out. So we're going to take our values and plug them in. So we're going to take our n times p, so our 1,000 times 0.02, because it was 2% of births, and we're going to get a 20, which is greater than or equal to 10. Then we're going to take our n times 1 minus p, not our standard deviation. We're taking the n times 1 minus p. So we're going to have 1,000 times 0.98, which gives us 980, which is greater than or equal to 10. So since both are greater than 10, the distribution of x can be approximated by a normal distribution. So we want to find now the mean and the standard deviation for the approximated normal distribution. So our mean, remember, is n times p. So 1,000 times 0.02 equals 20. And our standard deviation is the square root of n times p times the quantity 1 minus p, which gives us the square root of 1,000 times 0.02 times 0.98, which comes out to 4.427. And we're going to use these numbers to answer our next question. So now that we know that it can be used with a standard deviation, with a normal distribution, we want to know what is the probability that the number of babies in the sample of 1,000 born prior to 34 weeks will be between 10 and 25 inclusive, which means the 10 and the 25 will both be included in our answer. So we're looking for the probability that x is between or equal to 10 and 25. Now, in order to find the shaded area, we're going to have to standardize the points. But we're not just going to use the number 10. We're going to use the number to the left. Because remember, we have that 0.95, right? That 0.5, sorry, the 0.5. So 10 is actually 9.5. So 9.5 minus 20 divided by 4.427 gives us negative 2.37. Then we're going to do our B star, which is up at the top end. And we're not going to use 25. We need to do that 0.5 as well. So we're going to use 25.5 minus 20 divided by 4.427 and get 1.24. Now we're going to look these values up in our table and then subtract the probabilities. So we're going to take our B star minus our A star's values. So that's going to give us the 0.8925 minus 0.0089, which will equal 0.8836. So that probability would be about 88.36%. And so that is how you use the normal distribution to approximate a discrete distribution.